Hey guys, welcome back. Today we are continuing our conversation of the gas laws. We're going to learn two more of those today, which are Gay-Lussac's law and the combined gas law. So there's a little cheat sheet here on the screen for us and in your slides that just tells us the formulas for these different gas laws that we can use to refer back to them throughout this unit here at the end. So without further ado, let's go ahead and get started. First, we are focusing on the Gay-Lussac's law. So, who was Joseph Gay-Lussac? He was a scientist who studied the relationship between temperature and pressure of a contained gas at a fixed volume. So this particular gas law, we're going to be looking at gases that are in a fixed volume. So the container volume that they're in is not going to change, but instead we're looking to see what happens between temperature and pressure. So how do they affect each other? He discovered that the temperature in Kelvin and pressure are directly proportional, meaning that if temperature increases, then the pressure will increase as well, and vice versa. So Gay-Lussac's law states that the pressure of a given gas varies directly with the Kelvin temperature when the volume remains constant. So this is another one of those gas laws where when you calculate it, you have to make sure that the temperature is in Kelvin. That's one of the things that could be the trickiest in this unit, is that if you're working a problem and the temperature is given to you in Celsius and you don't convert it to Kelvin, then you can run into some problems. Okay, so here is this particular equation. So the pressure of the first gas over the temperature of the first gas, or the first conditions, I should say, is equal to the pressure of the second conditions over the temperature of the second conditions. Okay, so P1 and T1 are the initial conditions, and then P2 and T2 are the final conditions. So let's take a look at the example, because these are really plug and chug. We just have to use the problems to identify the variables and then plug them into the equation. So a gas in a sealed container has a pressure of 125 kilopascals at a temperature of 30 degrees Celsius. If the pressure in the container is increased to 201 kilopascals, what is the new temperature? Well, number one, we know that in this particular equation, the pressure and the temperature are going to be directly proportional, right? So if our temperature is increasing, or if our pressure is increasing, then we can expect our temperature is going to increase as well. Okay, so when we finish it and we get a look at our final answer, we should see that the temperature has increased. If that has not happened, something has gone wrong. Okay, so now let's identify our variables in this particular equation. So the gas is sealed in a container and has a pressure of 125 kilopascals. That would be our P1, because that's our initial pressure. And then our temperature of 30 degrees Celsius. That's our initial temperature, but remember, we're going to have to convert that to Kelvin. Then our pressure in the container is increased to 201 kilopascals, so that's our P2. And then we want our T2. So in this particular equation, we are solving for T2. Okay? So remember, to convert a temperature in Celsius to Kelvin, we just add 273. So our initial temperature is 30 degrees Celsius. So 30 plus 273 is 303 Kelvin. So that is going to be the value that we plug into these gas laws here. Okay? So now in this particular instance, we are setting up the problem to isolate our T2 and then plug in, or you can plug in your variables and then solve at the end. Personally, for me, that's what works better. It helps me kind of see where all the numbers go. Or you can do it with the variables initially, which is what has happened here. So remember, we're solving for T2, so we want to get T2 by itself. So in order to do that, we have cross-multiplied the T1 and the P2, right? So T1 times P2, which eliminates T1 on the left. And then in order to get our T2 by itself, we're going to have to multiply each one. So T2 multiply on each side will give us T2 is equal to our T1 times P2. And then, of course, to eliminate that P1, we would have to to divide by P1, which gives us this new equation. Again, if it's difficult for you to cross multiply and figure out the equation setup, you can always put the initial variables in and then solve, which is honestly easier. Okay, so if we plug in our numbers, so our T2 is equal to our T1, so our initial temperature in Kelvin, which is 303, times our initial, or times our second pressure, which is 201 kilopascals, divided by our initial pressure, which is 125 kilopascals, that gives us 487 Kelvin. So 303 times 201 divided by 125 gives us 487 Kelvin, okay? So let's check ourselves, because we know that this is a directly proportional relationship. So as temperature increases, pressure increases as well. We increased our pressure from 125 to 201, and we increased our temperature from 303 Kelvin to 487 Kelvin. So that checks out. So we did that correctly. Okay. And then if it wants the new temperature in Celsius, in degrees Celsius, I would be sure that on a quiz or in problems, I will definitely specify, do I want the temperature in Kelvin or Celsius? But if you need to convert it back to Celsius, you just go in the opposite direction where you subtract 273, which would give us 214 degrees Celsius. Okay, so now let's talk about the combined gas law. So this is your second law for the day. And so far with like Charles's law, Boyle's law, the Gay-Lussac's law, we've been looking at two variables, right? We've been comparing two variables. In the combined gas law, we're going to be relating three variables, okay? So it can get a little bit more tricky, but it's basically just a combination of all the gas laws that we've learned so far. So the combined gas law is obtained by combining Boyle's, Charles, and the Gay-Lussac's law. Dalton's law of partial pressure is not involved here. That was just a simple one that we learned at the beginning. So really we're just focusing on these three that deals with two different variables. Okay. So the variables that we use in gas laws are the volume of a gas, typically in liters, temperature in Kelvin, which is our degrees Celsius plus 273, N would be the number of particles, moles, those are mole conversions. We did those back in stoichiometry, so we're not really going to focus on those right now in this unit. And then P is pressure in atmospheres. So the gas laws may be combined into a single law called the combined gas law, which relates two sets of conditions of pressure, volume, and the temperature by this equation, which I'm going to show you here. So P1 V1 over T1 is equal to P2 V2 over T2. Okay, so that's where pressure, volume, and temperature initial conditions, and then the P2, V2, and T2 are under those secondary conditions, so final conditions. Okay, and just like in the Gay-Lussac's law, our temperature is going to have to be in Kelvin. So first thing I would do when you're doing these problems is double check and make sure that your temperature is in Kelvin. Okay. So this again is showing us how we can isolate variables. So again, these can be done in one of two ways. You can figure out what variable you're solving for first, isolate it, figure out the new equation, and then plug everything in, or identify your variables, plug the variables into the original equation, and then solve, okay? The second way I find is easier because when you have the numbers in there, I just find that it's easier in order to kind of identify it mathematically. But if you're someone who, you work with variables a little bit easier than you do with numbers, you can do it where you isolate the variable first, okay? So like, for example, this is showing us how we can isolate for P1. So if we were looking for the initial pressure in a combined gas law problem, and it shows you how to cross multiply, etc. Okay. To save us time, I'm just going to move forward and do an example. But if you want more help with just identifying the variables and solving the equations that way, let me know and we can definitely go over that. Okay, so let's take a look at an example. It says a balloon is filled with 25 liters of air at 1 atmosphere pressure. Now that's at standard pressure. So there's something called standard temperature and pressure, which is 1 atmosphere and 273 degrees Kelvin, okay? So that is something to keep in mind. I would make a note of that somewhere. In your assignment today, the standard variables are going to be at the top of your assignment, but you also want to just make note that standard temperature and pressure is 273 Kelvin and 1 atmosphere of pressure. So it says if the pressure is changed to 1.5 atmospheres, what is the new volume? Okay, so the first thing we want to do, and I'm going to exit out of this so I can actually do it in a little text box here. The first thing we always want to do is make sure that we have our variables and we know what we're working with, right? We want to know our variables that we need to identify. So with our combined gas law, there are 3 variables for each one. So we need our P1, our V1, our T2, and we need our P2, we need our V2, and we need our T2. I said T1 over here, and I wrote T2, so let me do that. Okay, so our P1 is going to be 1 atm. Okay, so atmospheres is pressure, so our P1 is 1.0 atmospheres or atm. Our V1 is 25 liters, and it doesn't tell us our temperature here. Okay, so if you're doing a combined gas law, you have to have the temperature. In this case, we're not given a temperature. You can be, so you could be given something in Celsius that you have to convert, but in this case, we're talking about standard temperature and pressure, so your temperature is just going to be 273 Kelvin. Okay, so 273 Kelvin, which will also be the case for this side of the equation as well. Okay, our pressure is changed to 1.5 atmospheres, and our V2 is what we're looking for. Okay, so now we have all of our variables, then we can plug this in. So let's go ahead and do that. I'm going to insert a new text box and do it over here. Okay, so our pressure 1 is 1 atmosphere, and our volume 1 is 25 liters. Okay, and should have done this as an equation, but we'll be okay. All right, and then that would all be over our T1, which is 273 Kelvin, and that is equal to our pressure 2, which is 1.5 atmospheres, times our V2, which we're trying to figure out, all divided by our 273 Kelvin. Okay, so since our 273 Kelvin is not changing, we can go ahead and eliminate that because it's divided by 273 Kelvin on the same side or on each side. So if we multiply, that just leaves us with our top. Okay, so that's 1 atmosphere times 25 liters is equal to 1.5 atmospheres times our V2, which is what we're trying to solve for. Okay, so if we plug this in to our calculator, we're going to have to divide by 1.5 on each side to get our V2, and then we will get our volume. So let's go ahead. We'll do 1 times 25, which is just 25, divided by 1.5. So let's go to our calculator. So 25 divided by 1.5 is going to be 13.888, so we'll round that to 13.89. Okay, so our answer here, our V2, is 13.89 liters. Okay, because our atmospheres eliminate and we are left with liters. So again, if it's standard pressure and standard temperature, standard pressure is 1 atmosphere, Standard temperature is 273. If the temperature is not given to us,